So we are going to talk about multiple linear regression and also spend some time on interpretation of model coefficients in a few different situations, and very briefly look at what are the assumptions of multiple linear regression, some diagnostics and efficacy measures. There is a data set available which has variables such as volume, area, weight, and cover. And these are like first few rows of that data set. So you can see volume, area, and weight are basically numeric data, and cover is a factor type of variable. So the cover of the book could be hardback or paperback. When we plot this data, identifying whether the book has a hard or paperback cover, so you can see that there are some differences obviously. So slopes are shifted up or down depending on whether it is HP or PB. And this is a weight against volume. If you look at the pairs panels, we can see that volume and weight, it has positive linear pattern very clearly, and correlation coefficient is also quite high, plus zero point 0.9. If you square it, it is like 81%. 81% of variability in book weight is being explained by just one variable, volume. And area somehow has, it's everywhere, like it's it's not very clear cut that it has any strong relation. But with weight, you can see 0.36 is the correlation coefficient. So this is the plot. And area versus volume, it's almost zero. It looks like zero here. So if you do multiple linear regression now with weight as response variable, volume and area as independent variables, and this data is all backs. It's not a huge data set, 15 rows of data. So we can get summary of this model, summary M. We can get estimates of the intercept, volume, and weight coefficients. But we find that intercept is not statistically significant. Volume and area are. When you do ANOVA for this model M, so this is what we get. So now we have residuals are 12, because if your total data points are 15, so 15 minus 3, one for intercept, one for volume, one for area. So you lose 3 degrees of freedom. So 15 minus 3 gives you 12 for the error. So looking at these two, we can make some observations. P value for area in ANOVA and regression should be close. We are talking about the second variable after volume. Second variable is area. So the p values you can see 0.0061, 0.0061. So those values are supposed to be close. But p values for volume will differ if there is a correlation between volume and area. The difference is not much, actually 7.02, 7.07, and 10 to the power of negative 8. So this is not very different, and one of the reasons is we saw correlation between volume and area was not all that high. When we have model M, we have seen earlier also, you can very easily get confidence intervals for the coefficients, intercept, volume, or area by simply doing conf int, so confidence interval, and that will give you confidence interval for beta 0, beta 1, and beta 2. So this one, negative 104, to positive 149. So that's the confidence interval for the intercept. It's very wide. And for volume, it is between 0.575 and 0.84. So standard error you can see is quite small, 0.06. So the variability is also quite contained. And area 0.246, 0.679. Now from this data, if you want to figure out the confidence interval for volume, so although we can get it very easily here, but the calculation is very straightforward. We take the point estimate 0.708 and then plus minus use t value for the 95% confidence and also degrees of freedom. So degrees of freedom here you are going to have is 12. So that should give you 2.18 and then the standard error. So standard error is 0.0611 roughly. So if you do that math, that should give you 95% confidence interval for volume. Also, another thing we can get along with summary, when you are printing this summary M, if you put a comma and also say correlation equals true, it will give you correlation of coefficients, and that's very helpful in figuring out, like in this case, intercept is not statistically significant. And you find that intercept has negative 0.88, so quite high correlation with volume. Now, if you think logically, if the volume of the book is 0, the way, like keeping area constant, so for the time being, if we forget about area and keep it constant, so if volume is 0, so weight is obviously expected to be 0. So intercept doesn't make much sense in this example, and it is not statistically significant, and being there it is creating problems. So it is having these correlations with volume, especially negative 0.88. So the best way to get rid of all these issues is to throw out intercept term. So we'll do that. But if you look at ANOVA, so I had shown you similar pattern for simple linear regression situation where you have only one independent variable and one dependent variable. But in multiple regression, if we have p variables, p independent variables, so this is how your ANOVA table is going to look like. So total degrees of freedom is always n minus 1. Your sample size minus 1. And you get p from here. So residual is always difference of the two. So you get n minus p minus 1. And then you can figure out sum of squares and mean squares and F ratio. But why we do ANOVA for multiple regression, and why it automatically also gives you one F statistic. So this is the same thing that you get from the ANOVA table. The reason is that for multiple regression, you can have so many different independent variables. So let's say if you have 100 independent variables and you are doing a t-test for each one of those independent variables, and you are doing, let's say, at a 5% level of significance or with 95% confidence level. So even just by chance, it can happen that 5 variables which are not statistically significant really turn out to be statistically significant, because there's a chance that we go wrong 5 times out of 100. So when you have a lot of like t-test, lot of p-values, that problem always comes up. But when we are doing this F statistic, we only look at one p-value, and what are we testing? Our null hypothesis is that beta 1, beta 2, up to whatever betas you have, they are all zero. So they do not have any impact on the model. And alternate hypothesis is that at least one of them is non-zero. So at least there is some value hidden in those independent variables. So we cannot simply throw them out. So at least one of them is non-zero. So you can get that answer very quickly if there is anything worthwhile or not when you are dealing with a lot of independent variables. So that's what you get from the F value. So if we remove the intercept for the problems that I mentioned earlier, and it's very simple, we just need to do -1 and then add our independent variables. So you can see intercept is gone. And what you will notice is that our standard errors now are lower compared to what we had earlier. So now you have 0.027 for volume compared to 0.06. So it is cut by more than half. And the reason you had that standard error high last time was because of this high correlation between intercept and the volume. So that was very high. And with area also there was a little bit, and you'll see that 0.10 also reduces to 0.09. So there is a little bit of improvement in our estimates. If you look at the diagnostics plot, this is a small data set. One thing that stands out probably is sample number 13. Residual seems to be very high compared to the remaining group, but remaining group doesn't pose any major problem because this red line is very close to the dotted line. On the normal QQ plot too, this 13th observation stands out. That book looks like is a bit different than the group. And 13 also is flagged for scale location plot. It also falls within 0.5 and 1 of Cook's distance on the leverage plot. So there's definitely something going on with that number 13, and that's something to be looked into. If there is an error, if it is found there is an error, then it has to be corrected. If it is not error, then sometimes people do this analysis two ways, one with and other without. If you are doing without a data point, and let's say you're writing a research paper, it's always good idea to mention that. So you remove this data point from the analysis. So there must be some valid reason given for doing that. Now coming to interpretation. So interpretation we have seen for simple linear regression is quite straightforward when x and y are as it is. So for example, if this is the situation, we say when x is increased by 1 unit, y is expected to change by b1. Suppose we had an equation something like this, where weight is the dependent variable and volume is the independent variable. So we would say when volume is increased by 1 cubic centimeter, so that's the unit of volume, book weight is expected to increase. So increase because we have plus sign, increase by 0.7086 grams. So we have this y equals, so this is estimate of beta 0 plus beta 1 x plus some error term. If we increase x by 1, so let's call our response some new value of y. So this is what we'll get. So we are going to get beta 0 plus b1x plus beta 1, and this part is nothing but y. Essentially you have y new minus y equals beta 1. When we are increasing x by 1 unit, your y is changing by beta 1. Now let's consider a situation where, due to whatever reason, we have to take log of y. Now we have this situation, log of y new is beta 0 plus beta 1 x plus 1. So you have seen that becomes log of y plus beta 1. And if you take log of y to the left, log y new minus log of y. So whenever I'm saying log here, it's natural logarithm. So when you take difference of y new and y, you end up with y new divided by y equals beta 1. If you take exponential of both these sides, you are going to end up with e raised to beta 1. For better interpretation, if I simply do minus 1 on both sides and multiply both sides by 100, you get something like this. So basically, percentage change in y, 100 times e raised to beta 1 minus 1. So what it means is, if I have a situation where response is log y, then if x changes by 1 unit, you can see the interpretation is now slightly tricky. So now I have to say the response will change by this much percentage. So when log is y, our interpretation would be when x is increased by 1 unit, y is expected to change by 100 times e raised to b1 minus 1 percentage. And we use expected because we are talking about the average or the mean. Suppose for a data set we have this model, then we would say when volume is increased by 1 cubic centimeter, book weight is expected to increase by about 0.118%. Similarly, if we have a situation where we take log transformation for x variable, and we can do a similar math, and we'll find that when x is increased by 1%, y is expected to change by b1 times log of 1.01. So with this model, our interpretation will be that when volume is increased by 1%, book weight is expected to increase by about 4.797 grams. Similarly, if we have log transformation for both y as well as x, so we are going to say when x is increased by 1%, y is expected to change by 100 times 1.01 raised to b1 minus 1 percentage. With this model, our interpretation will be when volume is increased by 1%, book weight is expected to increase by about 0.8226%. So slightly at a lower rate. Now let's move to RStudio and go through some codes. Mainly we'll use these three libraries. I'm going to run this. The data that I was using in the PowerPoint was all backs. So you have 15 observations and 4 variables. And then we made this scatter plot using ggplot2. I also added lines there, so I'm going to add GEOM smooth with SE equals 0. By default, it tries to have a non-linear pattern, but we can say method equals LM. So because if we did not separate them as per the type of cover as you see in the plot, you'll notice that there will be a lot of variability. So although in our model we have not used cover, but at some point we are going to use it. The only reason I didn't use it here because it's a factor variable, and I want to discuss few more things before I include a factor variable in the multiple regression as a variable. And then we looked at this pairs.panels only for the first three numeric variables. So even looking at the histogram, we don't really see any major issue. Like volume doesn't look like very heavily skewed. Similarly for weight, area doesn't have many points. So there are a lot of points here and some points here, and in between there's a lot of gap. And then we created this model by just adding volume and area with a plus sign, and then we did the summary. Now, one thing which is very common with multiple linear regression is finding this R square. Like if you make different models, and R square gives you a way to compare those models. Now, assessing the models, many times we want to look at how the predicted and fitted values behave. So let me do some predictions here and save that in P. So I'm going to use this linear model M, and we'll do predictions for all backs and store them in P, and then plot them. So let's put predicted values P on the y-axis, and on x-axis we'll put actual response, all backs, $, weight. What should we expect? Like, what is our hope? If we are making a model, we are predicting or estimating response values using our model. So between the two, between predicted value and actual value, what should we expect?
Good fit. Good. Should be a straight line.
Should be a straight line, positive or negative, or it doesn't matter?
Should be positive. Positive one.
Is it possible to have a negative uh, pattern between predicted and actual values?
Got a really bad model.
What's that?
If you have a really bad model, I suppose.
Okay, so if it is too bad, yeah, that's right, yeah. So we should not expect any negative correlation between these two, because it's not the question of relation between x and y. So this is actual response and predicted response. So they should always be positively linearly related. Looks like it does a decent job. If you find R square, if you do correlation between these two, predicted value and actual value, and if you find the correlation and square it, so that value is your multiple R square. 0.9825 is the value between P versus actual. So we can get that very easily. If you do correlation between P and all backs dollar weight, you get 0.963. So that's the correlation coefficient, and when you square it, that becomes your R square. So let me put this in C, and then we can say RSQ, something like that, is C square. If I run this line and then I select RSQ and run, so that will give me that value that I'm looking for, this multiple R square, 0.9285. That's the same value. But in R, if you want to run a line and also look at the output, what you could do is you just select the entire line and put a parenthesis. Automatically, it will put parenthesis at the beginning and also at the end. So when you run this type of line, it will not only calculate square of c and store that in R square, but also print it. So it does that as a two-in-one kind of situation. Whenever you have this kind of situation where you also want to look at the output, you don't have to repeat something. You just put parentheses at the beginning, at the end. That should do it. This is how you can calculate multiple R square in multiple linear regression situations. Because once you develop a model and you have P versus the actual response, and you find the correlation between those two and square it, you get R square value. But in any case, like even this summary gives you R square value very easily. For confidence interval of coefficients, this is how we got it. Confidence interval for M. Just to refresh like how it works. So I gave you that formula of B1 plus minus T times the standard error. So if you have a summary like this, where your estimate is 0.70821, you can find first of all a T value. Okay, let me use that trick. Parenthesis T and QT. For 95% confidence, the probability I'm using is 0.975. Degrees of freedom for the error is 12. So I put that 12. So this is my value of T. So we take B1. If I want lower interval first, so minus this value times the standard error, which is this. So that gives you a lower limit of 0.575, this number here. And the other one is 0.84. So instead of minus, if you do plus here, you get that. So these are like how you are calculating those numbers, but confidence interval for M, that will automatically give you both lower and upper. So one of the reasons we removed intercept was that it's not statistically significant, and also we know that it makes sense to remove it because if the volume or area is 0, then there's no point in having an intercept value for weight. So we do that by doing -1. If you run that and then do the summary, so this is what we had seen earlier. But let's also do that diagnostic plot. 2 rows and 2 columns. Says MF rows is not a graphical parameter. So I think it should be MF row, not rows. And when we do this, it's also important to come back to 1 by 1 so that if we plot feature plot, it doesn't look like small. And we had noticed in PowerPoint also, book number 13 is unique and it's getting highlighted almost in every plot. I'm not saying that anytime you have any suspicious data or it is flagged in all the plots should be removed. So there has to be investigation. You look into it. Is there a possibility of data entry error or something like that? So only when there is a valid reason, we can try running the model without the 13th book. And we can do that very easily. We can say in our data set all backs, so we want to remove row number 13. So we can say -13 for the row and then put a comma. After that, if you don't mention anything, it means all the columns. You run that, so there's likely to be improvement in some of the metric. But now if you again do the diagnostic plot, obviously 13 will not be there, but R flags other data points. And then in the Cook's distance, earlier also we had seen book number 11. Residuals, it's at the borderline, but it's not that bad. 11 is actually on the line here. And here also it seems to be part of the group. But Cook's distance is almost 1 now. And with this small data set, we should not be like, we should not go overboard with removing data points one by one, because something will come up all the time. But if you look at 11, 11 is not that bad if you compare with what was 13 trying to do. So 13 was clearly some kind of outlier. It also had great leverage. So it was contributing to a lot of problems. But 11 is not that bad, and you'll have these kind of data points in every data. Another thing I want to include here, especially talking about log transformation. So let's look at inbuilt data in R. It's called air passengers. If you do, okay, let's do question mark air passenger just to see what is this. Very old data. These are monthly airline passenger numbers between 49 and 1960. Actually, it's an example of time series data. And the numbers that you may see are in thousands. So for example, if I run air passengers, so you'll see all these numbers here. January 1949, 112,000 passengers. February, 6,000 more, and so on. If you do histogram air passengers, okay, I did not run that line 1-1. So this is what you'll see. A histogram which seems to be right skewed. The tail is longer on the right side, and most of the values are concentrated mid to lower end. Also, if you do a plot, so this is a time series data because one of the variables is time, and you can see fluctuations, peak season, off peak season, and so on. But one thing is very clear, the variability has been gradually increasing. So this is a good example where log transformation may help. So if I do HIST log, so you will see that when you type log, it also tells you like at what base. And if you need to change the base for any reason, you can always change it. So I'm going to keep it default. So log air passengers. This one is without log and this one is with log. So you can see situation improves a lot by taking log in this example. And similarly, you can see for the plot. So you can see compared to the first one, the variability becomes more uniform across the years. So I gave you like a few different examples. Now the interpretation can be extended to multiple linear regression very easily. So the only thing we add here, let's say apart from volume, we also had a term for area. So plus B2 area. So in those situations, we'll say when volume is increased by 1% and keeping area constant, book weight is expected to increase by 0.822%. So I gave you one example with the air passenger data. Here is another example from the book with hill race example, where you have a data frame, small data with 23 observations and 4 variables. And first variable is DIST, which is distances in miles. And climb is amount of climb in feet. So this is for runners, like how long they are running and how much they have to climb. time is record time in hours for males, and time F is record time in hours for females. One thing you will see that you pick up any correlation. So for example, distance and climb. So this one here. So although it looks like there is a linear pattern and both variables seem to be related in a linear way, but lot of data points are concentrated at the bottom lower corner. And then there is like one here and then one extreme here, almost like an outlier. So that one point is so far away from rest of the points. And it's a similar story for other variables too. Distance between record time in hours for male, most of the data points are here, and then you have one point far away in the right upper corner. Same thing between climb and time, distance and time for females. So story is more or less same. Now this one is done with the log transformation on both x, all x's as well as y's. So you can see situation slightly improves because the point that was in the upper right corner is still there, but then other data points are pulling towards it, and it's not that much of an outlier like it was looking here. So the spread is much more even compared to the first one. So in this example, you see that log transformation is definitely going to help. So we did not even do a multiple regression with the original variables. We did it only with log. So we have taken log of time versus log of distance plus log of climb. And this is NI health data. All the three are significant, statistically significant, you can see. R square is about 0.9831 and adjusted R square is 0.9814. So not very far away. If they are like far away, that also indicates some kind of problem, but both numbers are close enough. And overall p-value is significant. So at least one of the betas is significant. In this case, if you look at 0.68136, what does it imply? So now I'm using the definition that I gave earlier for log-log transformations. B1 equals this implies for a given height of climb, given means we are keeping this constant. So for a given height of climb, when distance is increased by 1%, time for male runners is expected to increase by 0.68%. The time is going to increase at a slightly lower rate compared to increase in distance. 1% versus 0.68%. This one is whatever you saw on the previous slide. I have just repeated, same thing. In the second summary, the only difference is what is highlighted here. So instead of using climb, we are using climb divided by distance. So if you recall, climb is amount of climb in feet, like in the entire run, and distance is distance in miles. If you do climb divided by distance, you are averaging out the values in certain way, like you are looking at a much better variable than just the climb, because climb by distance will take care of distance also. Like if your distance is large and a given climb for a large distance versus given climb for shorter distance runs can make a big difference, because it will be much steeper if you have same amount of climb in a shorter run. So that will be more difficult than if it is spread out in a longer run. So when you run that, you will notice a few things here. Obviously there's no change, almost no change in the second variable. Climb and climb versus distance or divide by distance 0.46, 0.46. The coefficient more or less remains same. But what you'll notice is there is a big increase in the coefficient for distance by doing this. So 0.68 and now it is 1.14. And not only that, the error has come down. It was 0.05, now it is only 0.03. Other things are more or less same, but there is a big improvement in the coefficient as well as standard error. R square, there is no change. Other things, in fact, F value and other things are exactly same. So coefficient of log distance depends on other explanatory variables also. So in this case, you see how the second variable is used. Coefficient can depend on that.
Prof, right? Just quickly to interrupt. Somebody asked on the chat if you can go back to the previous slide. How are the units related in that? Because the climb was in feet, however, the distance is in miles. Should we be concerned?
So when we are doing climb by distance, so we are saying feet per mile. So how much you climb per mile. So that's meaningful, right?
Okay.
So when you're dividing something with some other variable, those two units need not be exactly same. But the way we interpret, we would say for the second one, basically we can name it as a gradient, for example. Climb in feet per mile. So how much a runner has to climb in terms of feet for every mile they are running. So that will make a big difference for a same climb, same amount of climb for a short distance run versus like 1 mile run versus 20-mile run. If a climb is same, so if you use climb as a unique variable, it's not really taking care of that. But when you divide climb by distance, so in a way it is trying to create a uniform kind of situation. So this becomes much more meaningful. So the key idea is that sometimes when we are doing multiple regression, we don't have to use independent variables as it is. We have to think in creative terms like what makes sense and how the model will be more interpretable. So Irish Hill Race, if you put a question mark with the dataset name, it will give you more details. So this was done in 2007. Northern Ireland Mountain Running Association contributed to this data, and they have other information here. So this is the structure of the data. So mostly numeric or integer variables, and the pairs plot that we saw. If you want to do log, we copy this whole thing. You can simply say log. So that will automatically convert variables into log and then plot. And this is our model that we saw. And if you want to do log of climb divided by distance, so this is what we had done, where beta increased and standard error reduced. Another thing you can calculate is the correlation between the two variables, distance and climb. Distance and climb, you can see correlation coefficient is about 0.78. But what about if we do for distance versus ratio of climb divided by distance? NI hills, and then correlation between log distance. Earlier, correlation between distance and climb, which were both independent variables, it was quite high, 0.78. And when we ran this model with modifying climb to climb divided by distance, so correlation between those two variables is very less. It has come down close to zero. So because correlation between the two independent variables has come down, and that improvement actually has gone into the explanation by beta, where coefficient has increased from the lower value to 1.14. So this is another explanation of why this coefficient increased. It increased because correlation between the two variables or independent variables used in the model, it came down. Okay, coming to mouse weight. So the data set we are using is called litters. So it has three variables, all numeric: brain weight, body weight, and L size. So data on body and weights, brain weights of 20 mice together with size of litter. So L size is litter size. So how many? So 3, 3, 4, 4. So you have different values of the litter from which sample was taken, and then what body weight and brain weight. If we say brain weight is the response variable, so that versus L size is negative. As litter size goes up, brain weight goes down. And brain weight versus body weight, so this one is positive. As body weight goes up, brain weight also goes up. So if you run this model with L size and body weight, so I have run the summary also along with that. So this is what you get. So two things that we have compared here to highlight something is when we did brain weight versus litter size only. So we are talking about this plot. You can see the plot is negative. That's why coefficient is negative here. But when we included body weight in the model as the second variable, you will notice that now between these two, the sign has changed. So that's something significant. The direction of relationship itself changed just because you added another variable. So how can that happen? So coefficient of L size changes from positive to negative if you like go from here to here, and other way if you come from there to here. So let me give you another example. So this is about SAT scores, where y or the response variable is SAT score. X1, X2 are high school GPA and X2 is time here. So if you look at this plot and see the overall trend, so clearly over the time, if time is one of the variables, you can see SAT scores are going up. So there is a clear cut overall trend which is positive. So the coefficient of time is likely to be that beta 1 or beta 2 is likely to be positive. But if you include the fact that for different GPAs, which are indicated by 1, 2, 3, and 4, so within that, so you can see when GPA is 1, when GPA is 2, when GPA is about 3, and when GPA is about 4. So for a given GPA, the trend is negative. So whenever we have that kind of situation, it can happen that when you add an independent variable, it may cause coefficient of the other variable to change from one to another. So if it is positive, it can become negative. If it is negative, it can become positive. So while SATs are generally increasing over time, the SATs are decreasing within each grade strata. So 1, 2, 3, 4, as evidenced by decreasing pattern within each of GPAs. So there was also a study by Renault and Tam. So they have argued that This is because of grade inflation. Over the years, people get more scores. So the sign of estimate for beta 2, which is B2, in multiple regression model, SAT equals B0 plus B1, GPA plus B2 time plus error, will be negative and might seem wrong, because you are seeing a increasing trend and it may look like something is wrong, but it is actually correct when you think about the held fixed meaning, in this case where GPA is held fixed. So if GPA is fixed at 1, clearly the trend is negative, or if GPA is fixed at 2, clearly the trend is negative. So in other words, the partial relation between SAT and time is a decreasing relation. On the other hand, the sign of estimate of B1 in the simple regression situation where you have only one independent variable, time, so that shows a positive relation because of the overall positive trend. So if you recall, I think one of the lectures we talked about Simpson's paradox. So it refers to reversal of signs of directional associations that sometimes occurs when data are aggregated. If you group everything together, if you don't differentiate between GPA of 1, 2, 3, or 4, you may miss the point that there could be a negative relation. So here the GPA defined subgroups, in that we see negative trends. So however, in the aggregated data, we see a positive trend. This is what explains a situation where sign of estimate of a coefficient or one of the betas can change when you include or exclude a variable. Okay, the assumptions for multiple regression. So mainly two here. For a given explanatory variables x1, x2 up to xp. So when you have number of predictors as p, the expectation or EY or the average of y is some linear combination of x1, x2 up to xp. So expected value of y is something like this. So the main assumption is that it's a linear combination. And second one is that the distribution of y is normal with mean EY and constant variance sigma square. And observations are obviously independent. So independent means like second observation does not depend on the first one. So any of the observations don't depend on what happened earlier. Just like a toss of a coin. If you toss a coin, you get head. So second time you toss it, you may get head, you may get tail. So that's why we call that experiment as independent. Like first and second, there's no relation. There's no reason, like if you get first result as head, there's no reason you cannot get head again. So those are like examples of independent. But there are also situations where two events may not be independent. Let's say from a pack of cards, if I take out a card, so let's say we want to say that what is the probability of getting an ace. So there are 4 aces in a pack of 52 cards. So the chance of getting an ace is 4 divided by 52. So 1 by 13. Now suppose you pick up a card and it is not an ace, but you have taken out a card. Now you are left with only 51 cards. So in your second experiment, chance of getting an ace will be 4 divided by 51 and not 52. So the probability has changed. So the outcome is no more independent. So what you get in the first trial, so in the second one, it depends on that. For example, if you got an ace first time, then in the second chance, your probability will be, because out of 4 you have already got 1, So it will be 3 divided by 51. So what you get in the first one depends on what you'll get on the second one. But here we are assuming that the observations are independent. If you want to apply everything perfectly, these assumptions may not be fulfilled in real life. So there will be some deviations all the time. Now, outliers and leverage points. So we have seen this kind of plot. This is for hill race example. And one of the races here falls within 0.5 and 1 of Cook's distance. See, these dotted lines are at 0.5 and 1. So anything beyond 1 is obviously, it has a significant impact on the model. And between 0.5 and 1, you can think of that as a yellow light. So outside 1 is like red light, between 1 and 0.5 is yellow. And even when something starts getting close to 0.5, it could be something to explore and check. So there's a change in model estimate when that observation is omitted. How these values are arrived at, it's very simple. You remove first observation, create a model and see how much impact it has on the coefficients, by how much your coefficients change. Then you remove the second point, third point, fourth point, and the one that gives you the maximum change obviously will be flagged, something like this. So measures the combined effect of leverage and of magnitude of the residual. Another way you can explore if values have big impact, you can find out standardized difference. So difference in coefficient estimates obtained with and without each observation. So basically, whatever estimate you had earlier and take the difference of whatever you estimate you get after eliminating a data point and also divide it by the standard error so that we get standardized differences. So for example, if our model is based on the all backs data that we used earlier, and then there is a function called df betas, difference in betas. So this one automatically does all the calculations for you. So for example, if the first one is removed, if the first data point is removed, so you know this is with all the data. The change you get in intercept is 0.008 after removing first one. So it doesn't have a big impact. Volume gives you this much. And in coefficient of area, the change is negative 0.1. Let me put this in D. And I want to make those plots MF row. So we'll do it side by side. So one row and two columns. So the first plot I want to do is for D, all rows, and let's do for the first column. And this is for the second column. Actually, we can do for all three. Let me go back and do it for the without intercept situation, because our intercept was not significant, and by removing it, you had seen that made big impact on the coefficients. So this time you have only two columns. So there you have a data point which is showing you more than value of 2 on the volume plot. So this is for volume, this is for area. And the scale here is like negative 1.5 to about 0.5 or slightly over that. So these points are okay. All of them are okay. And this also is very different, but it's not beyond 2. But this could be something which is suspicious. So this could be another way that could highlight suspicious data point, especially anything more than 2. These ones are all okay. Okay, now assessing and comparing regression models. So although like as we go deeper into multiple regression, we are going to do this like in much more detail. But just to be aware, when we are developing different models, how do we assess or how do we choose a model? For that, there are many metrics people use. R square is very common. I showed you in the beginning that if you find squared correlation between observed and predicted response value, so that's what will give you R square. Or like some people even prefer depending more on adjusted R square rather than R square, because R square, when you include more and more variables and your model becomes more and more complex, your R square keeps on going up, but adjusted R square starts to deviate from R square, giving you a warning that now you are doing overfitting. So many people prefer adjusted R square to R square, but R square, whether it is adjusted or normal, is very popularly used. And then we have AIC. So this is the standard formula for this. It's based on the sample size, sum of squares due to error, and how many predictors you have in the multiple linear regression model. So P is number of predictors. So what it does is it adds a penalty that increases the error when additional terms are added. So note that the model with the lower AIC is better. Now, if your P increases, instead of 2, if you are using 5 predictors, your AIC value is going to go up. So it has a penalty for adding more and more variables. And basically it is trying to say that a less complex model is generally going to be better. But then this formula tends to be something which overfits and ends up choosing a slightly more complex model compared to some other methods. So BIC is slight improvement over that. It's Bayesian information criteria, and it is claimed as an improvement over AIC, which tends to make it more complex. This one is an improvement that provides stronger penalty for including additional terms. So if you do P log of n, that's what gives you BIC. Other things remain constant here. And there's another variant of AIC. So BIC is also a variant, but another variant is malus CP, which is also very common. And especially when you are running these models on a computer using a program like R, all these metrics are thrown out and lets you choose whatever you like to use. And this is the formula. So instead of constant, you have TP minus n, your sample size. If you want AIC, simply do AIC and it will give you AIC value. But it will be more meaningful when we compare several models. So if you have 3 different models, then only it is meaningful. You look at 3 different AIC or BIC values and then see which one gives you significantly lower value.
Hi, Professor. I have a question.
Yeah.
So for the log transformation, like say on slide 11 with the hill races, I can see visually that they're not bunched, in the lower left corner. They spread out, but like I can see the visual argument for doing that, but what is the reason for doing the log transformation? Is it to avoid like high leverage points or outliers, or is it? Yeah, I'm just trying to understand why the log transformation.
With experience, you'll notice that people don't wait until after doing all the analysis and then looking at diagnostic and finding, oh, this is not working, or there is a problem, there is a outlier. So people usually who are doing this kind of analysis don't wait till that stage. when they do data visualization before developing the model, they try to find ways to make sure that later on there are less and less problems. And these visual techniques are like very easy because visually you can see something can be improved until waiting for like later on finding something out through diagnostics. We can run the model even with this. We can run the model even if it looks non-linear. So for example, this one is a special example where they are concentrated here and we make them spread out. And these distributions clearly look skewed, right skewed, all of them. So waiting till later on after making the model and seeing in diagnostics that there is an issue, it's always better to take care of that beforehand. Similarly,
Okay.
if
Yeah. Sorry, go ahead.
Similarly, if instead of like this type of pattern, if there was some kind of non-linearity, like the relation was somewhat non-linear in whatever way, so that would have been another reason for doing something beforehand until like waiting at till diagnostic stage and then seeing something and then coming back. You were saying something?
Sure. Okay. Yeah. Thanks for explaining that. Okay. So it sounds like in this case with hill race, the hill race is like even though it looks linear even before transformation, because the variables themselves are left or they're right skewed. It sounds like that because we see that in the pair plots, that there might be issues down the line. So to prevent those issues, let's just do the transformation now to avoid issues later. But in the case where you drew in green those graphs showing the relationships, those are more obvious heuristics to just do a transformation right away because we know that it's not going to be linear.
Yeah. So like in these situations where we know that the relation is non-linear, so it's not that multiple linear regression is like end of the world. There are no other methods that can model the data. So there are different methods available to work with data and address like different situations. There are methods that will work better with non-linear data, but linearity people prefer because it's much easier to interpret and explain, and many people they come to the same page. It's like less confusing. But where necessary, where everything else fails, where we cannot like transform a variable to straight line, or we cannot make a variable normal by using all kinds of transformations, then we cannot use the method. We cannot use a multiple linear regression method. We may have to use something else or non-linear techniques. But people go towards linearity because it is something which is easier, simple, less complex, and most of the time it works. So you'll find that many cases with little bit of like not total violation of all the assumptions, but little bit of deviating from assumptions, still we may find that linearity is more or less approximately okay. But in these situations, if transformation do not work, we may have to go to alternative methods.
Thank you.
Yeah, no problem.
I have one question, Professor. So
Yeah.
I found Simpson's paradox to be like an interesting thing, like how it can like throw off some models. So I was wondering if there's like a command or a diagnostic tool which can like highlight those variables which have that relationship, or is it something that has to always be like visually interpreted and scattered, or is there something, a tool that can like highlight that?
If there are those kind of issues, it's like smell of the flower. It will come out somewhere. So it is not necessary that it will come out only when we do data visualization. So it will come out even when, like I showed you the summary first, and I showed you that the coefficient changes the direction one time it is negative, one time it becomes positive. So that was like even before doing the data visualization. So it will tell you at some point or the other if there is some such situation. So it may tell you in the summary when you add more variables and suddenly you see beta changing. So now at back of your mind you can know that, oh, there's something may be happening here in the background. Or like usually people do data visualization before doing any detailed analysis or investing time in analysis. They want to look at various plots in various ways and think about it, like how should I approach it. So a lot of time goes into that. So I would say like things like that will not remain hidden. It will come out in some form or the other. Thanks everyone, and I'll see you after 2 weeks.
Thank you. Bye.
Bye bye. Good night.